Okay, thank you very much, and thank you for the organizers to inviting me on this beautiful conference. So the topic is here constructing skew field with special properties. In particular, I mean that it will show that the multiplicative group of this field will be finitely generated despite it is on infinite dimension of its center. Now, using geometric methods. Now, the geometric methods are used in combinatorial group theory when you impose certain relations, combinatorial restrictions on the relations, then you can then deduce properties of the group. Now, this is done via the analysis of the van Kampen diagrams. Now, because these combinatorial properties, for example, small constellation or generalized or graded small constellation, result in certain geometric properties of the van Kampen diagrams. Now, the question is whether something like this could be done, say, in rings. So we now give a ring by a certain generators and relators, but now relators as a ring. Now, and we question whether we can impose certain combinatorial conditions on the generators of the ideal, and then to be able to deduce properties of the resulting ring. Now, but this is a very general question. Before studying in this generality, it would be good to try to understand some simple cases, and this paper is just one such an attempt. So, first let me recall the construction of a van Kampen diagram. So what we do now, so what is a van Kampen diagram? If a group is given by generators relations, say X alpha and R beta, then we see it as a quotient of a free group by a normal subgroup. The free group is generated by the relators X alpha. The normal subgroup is generated as a normal subgroup by the relators. And this is the way we present the group. Now the question is, given any W inside the normal subgroup, what we can say of it. Because, of course, it is a product of conjugates to the relators or their inverses. Now, then we can take a corresponding bouquet of petals with a base point. Now, and then each of the regions here on its boundary cycle, we can read a relator or its inverse. And this will just show what are the way we conjugate it. And then we fold it. And then the result will be a van Kampen diagram. And then what happens? Then we read the van Kampen diagram around the boundary circle, so we can read this word W we started with. So this is a very simple idea, but it has profound algebraic consequences. Now the question is whether we can do something like this in a case of a ring theoretic situation. So, we will not deal with the general case, but it's a rather special case. So our ring will be the group algebra of the free group over the ground field Z2, just the field of two elements. Now this is especially convenient because then we can just identify the elements of this group algebra with their supports. Because we have only coefficient 0 and 1, so it will be just simplifying the. And actually, we need only this generality now. So we are going to look on an ideal I of this group algebra of the free group by a certain number of generators. So assume that alpha are the generators of the ideal I. Then each of them could be written as a sum of words where these are words in the free group. Now, and this, they generate the AI as an ideal. Now, then we can ask how it is generated as linearly. It's very simple. Just multiply this element by left and by right by arbitrary words, and take the linear. This will be linearly generating the ideal. Now, okay. So we look on a certain element in the LD, call it C. It could be written as a sum of these elements. Just we take one of the relators, multiply it by some word on the left, some word on the right, and take the sum. Now, for this situation, we will define now a certain graph gamma. The graph gamma will be a union of subgraphs corresponding to every gamma in this sum. So this graph, it will be vertices V gamma and E gamma. What is the set of vertices is just the support of this relation. So just the elements in the free group that participate in this relator. So this is a certain finite set of words, and this will be taken as the set of vertices of the graph V gamma. Now, and as an edges we will take just all oriented edges connecting different vertices of this set. So we have a full graph on this finite set. This will give us this graph gamma V gamma E gamma. Now we define the graph gamma as a union of all such graphs of all such gamma for the gamma participating in the presentation of the element C. So we have a certain graph. Now let us specify a certain path in this graph. So let sigma be a path in this graph, starting with edge with vertex V0, going through the edge E1, vertex V1, etc., until we finished in the vertex Vk. So we specified a certain path in this graph. Now, for each edge EI connecting Vi minus 1 and Vi, so both of them are words. Now, and then let me call the first word Vi minus 1 Vi. Then, because of the definition of the graph, we have the left side, maybe I'm just neglecting the possibility of cancellation, but not important now. We have left side. Now, one is one of the monomials participating in the relator, and this is another monomial participating in the same relator, and multiplied by the half, by the something on the right. So and now we consider this as a kind of a rewriting procedure. It means that we start with this word, and then we take here what is a reversal, and this is, we consider this as a kind of a reverse rewriting procedure. And then when we have the whole path, then we have a number of such diagrams, because if in each of them the word, so this will be the word V0, this one will be the word V1, this will also be the word V1, this is the word V2, etc. So we can glue them together. So when we glue them together, we obtain what we call the rewriting diagram. So the rewriting diagram here, it depends not only on the graph gamma, but a particular choice of the path sigma. So actually, it shows the process how from a certain element in this presentation of the element, we can just subsequently reach another element by a series of such reversals. Okay. And of course, it depends, it is not canonical, it depends on the path. So, another choice of the path will give another rewriting diagram. No, and then we will use the writing diagrams under specific choices of this path sigma as analogs of the Van Kampen diagram. So this is how we translate the geometric situation in groups into an analogous geometric situation in the rings. So this is just the general motto of this particular work. Okay. Now, and this is some general remark, it did not refer just to this particular question. Now we return to the question, we start with a group, with the group algebra of the free group of a ring, and the first thing that we try to do, let us have a certain word W in F. Now, and we look on the, we take an independent variable t, and we take the field of rational functions over t with the coefficients in Z2. So this is just a field of rational functions. Now, and we would like just to be able to define rational functions of our W and to have a quotient of our group algebra such that all these rational functions would be inside this quotient. So what is done here? It is just by a kind of, we can do it in two steps. For example, we can take the free amalgamated product of this group algebra with the field of rational functions when we identify W with T, and then on one hand we have the group algebra over cyclic group. On the other hand, we have the ring of Laurent polynomials, the isomorphic. So via this isomorphism, we take this amalgamated free product. And now we just take the following, just we apply a kind of brute force in order to take a quotient with the particular properties. It means that we will now, first let us consider all the irreducible polynomials in this field of, in the ring of polynomials over T. The degree of this is d lambda. And then we know what are the linear basis of this field over Z2. Just take all the powers of T and then the elementary fractions. So we take a dk where k is less than the degree of the polynomial divided by the power of pi of t. This is just a part of the calculus when we first need it. Now, and then we now take words v lambda, which are, say, words with very small cancellation. I mean the complicated words that their only small parts are common. So this is easy to construct. For example, x, y square, x, y2 cube, etc. It is very many ways to construct them. And then what we do, we just impose the relations. Here are the relations we impose, that we take a we substitute in this polynomial w, multiply it by this monomial minus 1. So in the quotient, v lambda should be the inverse of this irreducible polynomial. So just invert the irreducible polynomials by brute force. And then we have the quotient. Now, in the quotient, it is if this ideal is not the whole ring, then the quotient will contain an isomorphic copy of this field Z2 over W, and even more than this, all the non-zero elements of this field will be presented by monomials in the group. But this is only subject to the conditions that really I is different for Z2F, because we don't know in the values, maybe we use too much force, and then we generated ideal is the whole ring. So the main question is now to try to see that this is really not the whole ring. So this what our effort is now on this point. To do it, first we introduce what we call semi-canonical words. We will not need canonical words, we need just semi-canonical words. This analog comes from the situation in the groups, where for the small constellation groups, actually very small constellation groups, we can on one hand define the semi-canonical words, and then with more refined way to define canonical words, which will be canonical words uniquely present the elements of the small constellation group, but we do not need this, and we only need the semi-canonical words. The semi-canonical words, let me just describe it on the group side situation, group theoretic side, is much easier to define than canonical. And this could be done via a list of forbidden words. For example, let us take some measure L on our relators. So we assume that the full measure of each relator is 1. Just then we take the percentage of the relator will be taken. So let us take some theta some threshold. For example, 0.0, but it really doesn't matter just to imagine it. Now, and then we say that a word is semi-canonical if it does not contain big parts of a relator or of its inverse. What is big? That it exceeds the threshold, for more than, say, 90% of a relator. So what is a semi-canonical word? That is, does not contain any subword of the relator or any relator exceeding 90%. Okay, now we have two main properties of the semi-canonical words. The first, that every word could be presented as a semi-canonical word. This is fairly easy in the group case, just induction on the length. And the second is that if we have two semi-canonical words presenting the same element in the group, then we can have a one-layer, one-Kampen diagram between them. So we have one of them on one side, the other on the other side, and what is important, that it is only one layer. It may have or may not different connected components, maybe only one, maybe many connected components. Each connected component, we have these regions in a row, and this is the only possible structure of interaction between these semi-canonical words. Okay, this is a group theoretic situation. Now we seek a ring theoretic analog of it, and then we will define the semi-canonical words via also a list of forbidden words. So we're now going to state our list of forbidden words, that the word is semi-canonical, when it does not contain subword from this list of forbidden words. So let me now, it is important to stress, we will see it in a moment, that while the list of forbidden subwords in the case of group, it was invariant after taking an inverse. In this case, important, it will not be invariant under taking inverses. This is an important difference between the ring case and the group case. So first, what we have, A, just if we have, V lambda was one of our complicated words, which served inverse of the polynomial P lambda. So we divide it into three parts. So V lambda 2 primes is just a middle part of this relator. If its length exceeds the threshold, then it will be a forbidden word. This is part A. Part B, we take also, we look in a relator, and then we take also, now we assume that the middle part is small. Its complement exceeds the threshold, the sum of the part. So now, and then we take the words of the form. Here it is. The end of the relation, W to some power k, and the beginning of the relator, where k is outside our permitted range of it. It doesn't bother us if it would be 1 to d lambda minus 1, but all other values are forbidden. Just only the values that appeared in these elementary fractions are permitted, the rest are forbidden. Now, then the group C of the forbidden words is just, we don't want to have V lambda standing before W. Actually, they will commute because they commute as pre-images commute in the ring. But just we will put always W before V lambda, and if we have this, we avoid the situation. And the part D of the list of forbidden words is that we don't want to, for different lambda 1, lambda 2, have these words of their inverses one against one near the other, because we have the multiplication table of the ring. So we can just, they are equal as sum of the elementary fractions. So we don't need them, so we include them in our list of forbidden words. Okay, now we have defined this notion, so we know what we call a semi-canonical word, and because the list of forbidden words is not closed under inverses, so our list of semi-canonical words is not closed under inverses. Now, here we have two key statements. Lemma 1 is that every element in the quotient can be presented as a sum of semi-canonical words. It is an easy exercise, just looking on the structure of the ring and what we have done. Now, and the second lemma, this is actually, so let me, before I state the second lemma, just let me explain what kind of words could appear as subwords or semi-canonical. For example, what we have here is a fractional power of V. So we have maybe a big power of V lambda. Now, finishing by beginning of V lambda, starting with the end of B lambda, and some power of this word W, k, where k belongs to this range from 0 to d lambda minus 1, because it could be only in the first position here. So this kind of words are permitted to appear in semi-canonical words. So this is the difference between the group case, because then we could not have powers of the relators at all in a semicanonical word. Now the key statement is the following, lemma 2, that says that in this quotient, if we take the element 1, we cannot express it modulo the ideal as a sum of linear combinations. This is, our case is the same because we're working over the 2 of non-unit semicanonical words. Okay. In particular, if this is true, it means that I is not the whole. Just need this. Okay. And actually, in the whole statement, this is just rank 1 version of the main lemma. Now let me sketch the proof. So we assume that, contrary what we have thought, 1 plus the sum of non-unit semicanonical words actually does belong to the ideal. And these are mu are non-unit semicanonical words. Now we return to this graph gamma that we have earlier defined in this particular case because we have element of this ideal. So we define a graph gamma. Its vertices are certain words. Its subgraphs correspond to supports of these relations with all the edges between them. And then we take and we color the edges of this graph into green edges and red edges. In which way? Let me explain it. Because of the particular nature of this relation, typically it looks like the following. We have something on the left. Now we have this relation, something on the right, and here we have a sum of powers of W. So it means this is not just word, this word plus this word with power 0, accordingly to the coefficients of the irreducible polynomial. Of course, we can think that these are much, much longer than this W. Now, so in actually, if they have here some number of elements, so we have the subpart, if we have here L non-zero coefficients in the irreducible polynomial, the support will be of L plus 1 elements, one on the one side and L on the other side. Now, any edge between this and any of these others will be colored by green. Every edge between these we will color by red. So we just take the two coloring of this graph. And then we extend it to the whole graph gamma. Now, what follows, we would say that we will take the any path in this graph will correspond to a rewriting diagram. We will take now only passes that all of them are only from green edges. So we never use a red path, a red edge in our path. Now, and then, because of the particular form of the element, it has, we take a path, it starts with the element 1, because this is a part of this, and then we go, now until we, green path, until we reach an element which is its coefficient is 1, not 0, it could be 0, it could be 1, and we should end at the vertex with coefficient 1. It is always possible because if the coefficient is 0, it means at least twice we have two different relations with the same support, the element of the support. So also if we have closed subpasses, we can omit them. So finally we have a path starting with 1 and ending with some edge with non-zero coefficient. It means it actually is present in the element of the group now of this group ring, but now we also now we also have certain restrictions of how we choose this path. Now, because we have two possibilities. If we go from the side of it on, if we start on this side of it, so there's actually only one green path that goes to the other side. But if we start on this side, that we have many green edges that connect this. So now the point is, when we choose some such edge, it means that we add a new region to our rewriting diagram. We look, if this diagram for some choice of this green edge cancels out with an already existing cell, then we take it. Now, it could be just, it cancels out because it's a zero path between them. I mean, a path in the diagram which the label cancels out to 1. In this case, we take just such a choice. If we do not have such a region, then we just routinely take the value of k equal to 0. So this is the two cases. Now, here is some delicate point, because if at present this region doesn't cancel out because it's a no zero path, it could possibly happen that after adding some more things that would arrive a zero path but not existing here. Now, this situation is excluded using the convexity properties of Van Kampen diagrams. So we have to prove that if we did not have a zero path now, it will never appear in the future. So in this way, the resulting diagram will be non-reduced. So no reagents could be cancelled out in it. So this is the point. Now, when we have this, so we take the resulting Van Kampen diagram that is produced using such a path. Now it will be reduced. It have all the properties of Van Kampen diagrams, but the labels of the boundaries will not be the same because we have taken maybe different green edges, but it doesn't matter. In any case, it will have the small cancellation properties. Now, when it has, then we look around this path. So this will be one of the words presented in this sum of representation of C, and then because it will have it will have instead a forbidden word because of the properties of the Van Kampen diagrams. You can take it into levels, and the highest level will have a big sub-word of the relation, just a usual kind of Greenlinger lemma in this context, and this will give the contradiction. So the contradiction is, we assume that we have the ideal, it is not, because if we see that one cannot be expressed as a linear combination of non-unit semi-canonical words via modulus ideal, so the ideal is not all. So this is actually the rank 1 procedure. I describe it more or less the rank 1 procedure. I don't know how much time I have.
Still 10 minutes.
Huh?
Yes, 10 minutes.
Oh, even more than I need. Thank you. So now, when we have dealt with this range 1 situation, let me just sum up what we achieved now. So we know that the field of rational functions over W is isomorphically embedded in this quotient in such a way that all the non-zero elements of it are represented by monomials in the quotient. Monomials, the images of the words in the group F inside this factor. Now, we just have to repeat the situation in n stages. But now we just do the same, but now we assume we proceed by induction of the rank. So say we are in rank R, everything before rank R already was done and behaved as we wish it. So we have the ideas of while Ri each is bigger than the previous one, so we have a series of quotients. And now, and we know that all these fields are already embedded in this quotient. Now, and all their non-zero elements are presented by monomials in the quotient of the group algebra. Now we have to choose the next word WR for which we do the same procedure. Of course, we will take it is not conjugated to any element of the union of all these fields that we have dealt before, because we don't need them. And also it is important that we assume that this word is semicanonical. Actually, each word is not equal to a semicanonical. It will die a sum of semicanonicals, but we just take it step by step. So we just enlarge a number of steps. So the next word we take will be also semicanonical. I mean semicanonical modulo the previous. So for each of the previous steps, we had a list of forbidden words. We take the union of this list. A word is semicanonical in the rank R if it doesn't contain any forbidden word for all the previous ranks. Now, and then we actually repeat the same procedure now. And we claim first that we claim that every element could be presented as a sum of semicanonical words in rank R. This is an easy part of it. Now, and the main part of it is that if the one cannot be presented, this is lemma 1, the main part of it, that, this is the rank R version of lemma 1, and its proof is also routine, and the main part is the rank R version of lemma 2. And lemma 2 claims that 1 is not expressible modulo the next ideal Ri as a linear combination or sum of non-unit semi-canonical words, of course, in rank R also. So, and then we proceed the same way. We assume that we can present 1 as a sum of semi-canonical words modulo the next ideal. Now we construct the corresponding graph gamma. Also, we take the coloring green and red edges. We take a path exclusively of green edges, starting at 1 and ending on some vertex with non-zero coefficient. And then we have also looking that we do not take words that we do not take edges that would lead to non-correct cancellation of cells. Only if cancelled, that is cancels fully. So, and then we obtain now the rewriting procedure along this path will give us a certain graded Van Kampen diagram. And now, but let me say that in all these relators, the biggest part is V and the small part is powers of some W. And then this kind of Van Kampen diagram is especially simple. Usually dealing with graded Van Kampen diagrams is a difficult problem. In this case, not, for the following reason, because we assume all these complicated small cancellation words are vastly different from another. Then by easy induction, we can show that there is no, all the contiguity diagrams, they reduce to direct meeting between the edges, because usually what complicates the theory of graded small constellations that we have to deal in some way with the contiguity diagrams. And here we actually don't need it. Now, but then the result is a graded Van Kampen diagram, with small constellation, and then repeating the same argument, we see that in some part it should contain some forbidden word. For some rank, not necessarily the highest rank, maybe for some rank, but this is enough, and this shows that we actually cannot present one as a linear combinations of new unit semicanonical word modulus the ideal. Therefore, the ideal is not the whole group. This is what we want. Now, taking the inductive limit of such groups in a particular choice of the W's, we obtain this construction. Thank you very much.
Thank you very much, Professor Rips. Are there any questions or comments?
And
Yes.
we have some possibility of having deformation theory
Excuse me?
in the context. Deformations. Because once you have algebras of the fields, we speak about deformations. We have some deformation theory.
I don't know. I have something about this. I want to, let me say, just what we started here, just in general, we are lacking an analog of small constellation theory in rings. Now, here is just one small example to show that in principle it's possible, but we took such a conditions that this is group bound. So actually one have to think what could be more general conditions, and this I cannot say now. Let me say also, I don't know, it would be nice to define a hyperbolic ring. I don't know the general definition. I just, what we deal here should be examples of hyperbolic
We
rings.
don't have hyperbolic, we got deformation.
I don't know, but so for your question, I don't know.
What you want, your condition kind of, you have a ballistic condition to be stable under at least infinitesimally small deformation, right? The kind of generic conditions. But if in this introducing fields, especially if you introduce fields with more kind of freedom left, functional fields, if there is a chance for having a deformation theory. Imagining you have small cancellation group, then you deform it and you get small cancellation ring in appropriate field. The field is large enough, maybe you can do it.
What do you mean deformation?
Yeah, the deformation, we have fields you can deform, yeah, man. That's the whole thing. Yeah, you have moduli. You have field, you have algebraic geometry, you have deformation.
No, I don't know. I don't think so. I don't know.
Is there a question? Yes.
How much does the construction depend on the ground field?
Oh, it just will be complication. Actually, you could do it over every countable field, but then you need to take much more care.
Any other questions? I don't think so. Let's thank Professor Rips again.
Thank you very much.